Pretty sure this is the topic, these next two topics, my recordings, I don't remember, one of them it's like there's no image recording, and some of them I think, no, the next one does have a recording, but I did change it a little bit, because when I originally gave the lecture for the next topic, optimization, I did a lot more than I do now, so there's like extra information in that one.
I couldn't really do a lot of things, so I usually look back on the notes that I take from the previous lecture, and since it was just you talking, it was just kind of...
Yep, I don't have recordings for it. They didn't work both times, so that is how it is. But you can watch this one. So the next topic is linear algebra, and this is a topic that is new. So I've been doing it now for the last year. I've done it for 2 semesters. And I added it because at MSU you guys don't take a linear algebra class, and that is very much too bad because it's a really, really important class for engineering, and it's part of the requirements for ABET is that you have linear algebra. ABET is the accreditation board for engineering schools. So what the idea was is to try to incorporate linear algebra into other classes so you can at least see it, since you're not taking a full math class on it. But a lot of people, just so you know, as you're picking your PEs and stuff like that, a lot of people do choose to take linear algebra as one of their PEs. There's a linear algebra math class, which is all like theoretical. Not theoretical, but it's not using the computer at all. And then once you take that, you can take a numerical linear algebra class where you learn all the methods for linear algebra. Linear algebra is basically essential if you want to do anything with modeling, the computational side of linear algebra. But linear algebra in general is essential for every single class that you take. And I say this all the time, that engineering classes exclusively rely on solving systems of linear equations and like a tiny bit of calculus, like just the littlest bit, like that you can take a first derivative. Do you know what I mean? Like maybe integrate one time. So the math that you see isn't really super complicated, but linear algebra is every engineering problem you do, you get all of the equations that apply to that system, you count your number of unknowns, you make sure that you have that many equations, and you solve the system. Every single class, that's what you do. And I find that engineering students often get to this point where they're just like plugging things in and trying things out, and they can't find what the solution is, and you look and you're like, well, you don't have enough equations, you have more unknowns than you have enough equations, this isn't solvable. And it all relies on this very simple concept of linear algebra. And so what we're going to be doing in this topic is both looking at how you solve these systems in MATLAB. So I'm going to write a general system of equations, and we're going to use this notation throughout. And then you're also going to be writing the algorithm one of the algorithms. There's a ton of different ways to solve systems of equations, and I've just chosen the simplest one, and in 303 you're going to do a lot more of this. So the notation for linear algebra systems is that you have an equation that has n number of unknowns, so that's why you see x of 1, x of 2, all the way up to x of n. Each of those unknowns is multiplied by some coefficient, and the coefficient is numbered by its unknown and by its equation. So you can see that these a's all start with 1 because it's equation 1, and then the second index is the unknown that it's at, so it's x11. You'll see this notation is chosen because of the way that the matrix is numbered in MATLAB. So this is first row, first column, this is second row, first column. And so it makes it so that you can adapt it pretty easily. In order to be able to solve for all the unknowns in a system of linear equations, you need to have the same number of equations. So we have n unknowns, we need n equations. The right-hand side of the equation is for any term that doesn't have an unknown in it, which we just use as the variable b. These are linear equations, so all of the coefficients are constant. If they depended on an unknown, then this wouldn't be a system of linear equations, and so these methods wouldn't work. And then all the b's are also, they have to be constants. And so n is what we use for both our number of equations and unknowns. So we're going to look at several different ways of solving this system of equations that are already programmed in MATLAB, and then we're going to program one of them that isn't available in MATLAB. The only thing that I have learned through not just this class, but all the classes that I've taught, is that one of the things that students are coming in with very different backgrounds is matrix algebra. And whether they've seen it before at all, whether they've taken a whole class on it. I learned it when I was in high school, for sure. I remember solving system of equations on my calculator endlessly by programming them in with the matrix, but it doesn't seem to be a consistent thing. So let's just talk first about matrix algebra, not with linear algebra, just to make sure that you remember how matrix algebra works. So I'm just going to give an example. If you have two matrices and you multiply them by each other, the matrices' inner dimensions must agree in order to do the multiplication. So that's why this is what the asterisk is reserved for in MATLAB. So if you ever try to multiply two arrays by each other and this dimension match isn't true, it's going to throw an error versus the dot multiply. So I showed that when I first introduced the dot multiply. But if you want to just do this matrix algebra, you take the first row and multiply it by the first column, and it goes in the first spot. And the dimensions of the result of the multiplication will just be the outer dimensions of the multiplication. So 3 by 2, the two inner dimensions cancel. So for the first multiplication, you're going to get 3 times 5 plus 1 times 7. So that's going to be 22. And that's this row by this column. This spot here is going to be the first row by the second column. So it's going to be 3 times 9 plus 1 times 2. So that's 29. And then, I'm not going to do the whole thing, but then this next spot here is the second row by the first column. So it's 8 times 5 plus 6 times 7. And that comes out to 82. And then I'll just fill in the rest. So make sure that you first understand this basic idea of how matrix multiplication works and how this is not, or how this is what the asterisk operator is reserved for. Okay. Now, as far as solving systems of equations using matrix algebra, you need to be familiar with the inverting a matrix. So, inverting a matrix is sort of like dividing by something, and when you invert a matrix and multiply it by itself, it equals the identity. So that means if you had a matrix equation here, where you have a matrix A times X times equals B, if you wanted to solve for X, the only way to do that would be to multiply both sides by the inverse of A. And then this here would become the identity matrix. The identity matrix just is all zeros with one on the diagonal. And so that would get you to solve for x. You see some of this in your differential equations class once you get there, if you hadn't seen it in an algebra class previously. So this is sort of like equivalent to division in scalar algebra. So those are the two things that you really have to understand in order to be able to do this. So now what I want to do is show you, do I have room for this? Yeah, I should. Now show you how you're going to use this matrix algebra. So the way that we use it is we rewrite systems of linear equations in matrix form, and that allows us to take advantage of matrix algebra in order to solve the system. So as an example, let me give you a 3x3 system. And I'm giving it to you in its friendly form where it already has everything algebraically separated and stuff. Typically, you have to do this step on your own. Get like all the variables in the right spots. So these are my three equations. I have 1, 2, 3 equations, and then my three unknowns are x1, x2, x3. So to write this in matrix form, you are going to take advantage of matrix algebra, which I just showed here, to rewrite all of these three equations. What you do is you put all the coefficients in this first matrix. So we have 3, 2, and 1 as the three coefficients in the first equation. And then the unknowns are x1, x2, x3. So you can already see that if you multiplied this matrix by this matrix, you would have this row times this column, and it would equal the left-hand side of the first equation, because matrix algebra does 3 times x1 plus 2 times x2 plus 1 times x3. And then it's going to equal the constant on the right-hand side, which is 2. So once you get it set up in this form, it's pretty easy to build the matrix. You just put in the coefficients in this first matrix. If the variable is not there, then you give that coefficient a 0. And then you put the b values, or those constants, in its own array on that side. And this is standard notation across all linear algebra, both in math and computational applications of linear algebra, is that this is A, this is X, your unknown, and this is B. And technically, you should indicate that these are arrays by either bolding them or putting the double underlined or overline is for a matrix, and then if you want it to just be a vector, you can just put the vector symbol. But we typically don't do that. We don't do that in a lot of the computational classes because linear algebra systems are always this. They're always ax plus b, so it's just known that that's how they're set up. So as you can imagine, that this is an example, but all of the algorithms that I'm going to be showing you and using is going to be doing it for any system, right? So if you wanted to write this for any system, and that the example I'm going to give you today is going to be a 3x3, so that's what I'm going to write it for this one. We're just going to write this in general for the A matrix where the A coefficients are numbered as I showed you before. So it just tells you which coefficient it is, basically, for which unknown in which equation. So when you refer to the algorithms that we're going to write out, just keep in mind that this is what they're referring to. And then the matrix equivalent is conveniently numbered the same way the array is in MATLAB. And if you ever need to use the help for linear algebra in MATLAB, they use the same notation. Okay, so let's talk about the three categories of ways that you can solve these systems of equations. Okay, so the first way is the inverting method. So this is the one I've already shown you. So if you have a matrix equation, ax plus b, I showed you that you can just multiply both sides by the inverse. And then all the unknowns can be found directly through the inversion of your coefficient matrix. So you guys should have seen somewhere how to manually invert a matrix using row reduction. You could do it on your calculator if you've never done that before, but once you get the matrix set up, you could do it. In MATLAB, the way to do it is that you first have to define all the variables as a and b, and then if you want to set x, you just use the function inv, plug in the input of the array that you would like to invert, so a in this case, and then you do matrix multiplication, so no dot, just the multiplication symbol, to multiply these two by each other. But if you ever use this method, MATLAB will provide a warning. It's not an error message, it's just a warning in the code that you wrote it. You'll see that little orange thing. Because this is unnecessarily expensive, it's not necessary to invert the matrix if you're trying to save on computational time. And so while this is fine to do if you're doing like a quick 3 by 3, 5 by 5, even like up to like 100 by 100, it's not going to really matter. But anything bigger than that is going to be too slow, so you wouldn't want to do it. So let me just show you with that example that I gave. So I'm going to define A first, and this is the example that I wrote out of that 3 by 3 system. So there's A, and then you do have to be very careful that all of your dimensions are correct. So B is a column vector, so it needs to be programmed as one. So I just write it out as a row and then transpose it. So there's my A and my B. So if I just type in what I just showed you, it'll solve the system of equations very quickly. I don't know if do the warnings ever show up here? Let me see if I can show you the warning. So define my A, find my b, and then call the inverse. Okay, so you can see here there's a warning and it says inverse of a times b can be slower and less accurate than this other alternative. Consider using it instead. So that's what I was talking about as a warning. The less accurate is because you're doing more flops, like more operations, and so there's more you're like, when you do more calculations, you have to truncate more often, so it's less error, but the precision of the 64-bit is like ridiculous. Like it's not even close to what would ever matter, but anyway, that's why it says that. So, so that's that. So that would be the inverting way. So this is really important because this is the point of this part of the class. In engineering problems, real engineering problems, you would never, ever, ever invert a matrix, because when we're using these methods for anything that it's important for, you do not have the computational resources to do that. So if you're doing a small system where you're just doing like a homework assignment, this is fine to do, but anything else it's not. So the next method I'm going to show you is an elimination method. And this is categorized as a direct method. And since we're not programming these direct methods or inverting matrices by hand, I'm relying on your previous background in math to kind of understand this a little bit more. But let me just show you an elimination method for a really simple one. So what I'm going to show you for is a 2x2. So this would be considered an elimination method. So these are my two equations, and they have two unknowns in them. So why don't you tell me some of the ways that you have learned to solve a system like this? Yeah, so solve for one of them and then plug it back in to the other equation so that you only have one variable left, and then back substitute it back in. And that is an elimination method. It's the Gauss elimination method that you can write an algorithm to do that for any number of equations, any number of unknowns. So to do that, we need to eliminate one unknown. So one way to do that is you could just subtract the two equations. It'll get rid of x2, and you can solve for x1. So x1 would be 4. Once, yeah. So the way that you guys learned it, you didn't learn it algorithmically, right? You just learned methods of solving two equations, two unknowns. So, but think about if you had to generalize that so that a computer could do that for any number of equations, any number of knowns. So what's that? That's called an elimination method. You're eliminating all the variables but one in one equation, and then you're back substituting them into the other equations. And for 2x2, you just think, oh, you're substituting. But if you think about it more generally, that's what you're doing. So first you have to work to eliminate variables from each equation. Once you've eliminated enough, then it's called back substitute because you go backwards in the array. But it's just substituting in. And then you can get the other unknown by substituting it in. So I'll just write that down. I think you guys have done that before. So if you generalize this algorithm, and this is what I used to have as part of the lab, is that you wrote this algorithm first and then you wrote the next one, but I removed it because there just wasn't enough time to do both. This is a really nice algorithm to write, but because it also is not used in engineering problems because it's also too expensive, I chose to use the one that's most realistic for modeling problems. So this one is also available in MATLAB already. And there's a couple options. To do this exact method that I just showed you, it's called Gauss elimination. You've probably also heard of Gauss-Jordan elimination, which is just worse than Gauss elimination. It's just more, it does more operations. So it's not even available in MATLAB. And it uses the, in MATLAB it uses the division operator, which is why you can't use a division operator on vectors. It's because it's reserved for this. No. No, it's not the division operator. Why did I write that? It's the opposite. Forwards, backslash, forward slash. Yeah, forward slash. So if you wanted to solve, it's just a, is that forward slash? I don't know. Whichever, it's the one you don't normally use. You know, it's not the division operator, it's the other one. So this one uses Gauss elimination. Gauss elimination does not invert the entire matrix because it eliminates however many variables it has to, and then it back substitutes. So it saves, it's like twice as faster than the inverse, which is not very much faster because it's not even an order of magnitude faster, right? So for problems where there's millions of operations, it doesn't really help you that much. But it's something that's been developed in math before these other methods were developed, so it does exist. So there's really no reason to ever use the inverse operator in MATLAB because the backslash operator, whatever this is better. And it does the exact same thing. They're both direct. There's no guessing. It directly solves it. There's another function that I wanted to show you, which uses another direct method that you may have heard of. You may program it somewhere along the way, called LU decomposition. It is the same exact idea as the elimination method. It just uses a different technique, and it is exactly the same it's computationally exactly the same as far as how expensive it is, but it's developed as a function in MATLAB called linsolve. So you give linsolve the A and B inputs, and it outputs the solution. Totally different algorithms. There's really very little similar about the algorithm, but the result and the expense is exactly the same. If you look at any numerical method textbook, like when you get your textbook for 303, both of these will be in it. Okay. I'm using these numbers very poorly. Sorry about that. So one option for the inverse, which is method 1. Method 2 is the elimination direct methods, which I've given 2 options, A and B. So let's move on to our final method, which is an iterative method. Now there are several types of iterative methods, so the one that we're going to be programming is called Gauss-Seidel. I'm having you program this one for 2 reasons. One, it is an easier algorithm to write than the other one. And 2, this is the type of method that's required for any big system of equations. Okay, so assuming that you have the same given, which is ax equals b, just as you would with either of the other two methods. This is how an iterative method works. Step 1 is you take each of your equations that you have and you solve for one of the unknowns. So for example, I'm going to do the 3 by 3. For the first unknown, you solve, or for the first equation, you solve for the first unknown. I'm not going to rewrite the equation again, so hopefully you can refer back to it. I'm just going to solve for it. So here, first equation, I solve for x1. Second equation, I'm going to solve for x2. And then the final equation, I'm solving for x3. So at this point, I'm just rearranging the equation, okay? So what you do is you rearrange, and then you provide a guess. For your 3 unknowns, or however many unknowns you have. So for the ones that I give you in the lab, you can guess 0 for, you can get it to converge with a guess of 0 for all of them. So you guess values for your unknowns, then you update those values using this equation here, these sets of equations, by just plugging those guesses into the equation. So then x1, x2, and x3 all have new values. And then you just keep doing that. You keep updating x1, x2, and x3, and then plugging them back into the right-hand side, updating x1, x2, x3, plugging them back into the right side. And that's why it's called an iterative method. It's just a guess and check method. It's not directly solving the equations. It's not eliminating and substituting in things. It's just guessing, seeing if it satisfies the equation. If it doesn't, it guesses again, or it updates the values and plugs them back in again. So the part of the algorithm that's important is when do you stop guessing, right? When do you know that you're close enough? So you're going to repeat that guess and check step A until x1, x2, and x3 stop changing. So if every iteration of your guess, if those values are becoming the same, then you know that you've satisfied the equation, and therefore you must have solved the system. Remember that any system of equations only has one solution. There's only one set of x1, x2, x3 that satisfies it. So if all your left and right hand sides are equal, then you have found a solution. So let's talk about what this actually means. So first, I'm going to, and this is what I recommend that you do, I'm going to store all of my unknowns in an array, just like you do when you solve using an intrinsic function. So if I needed an x1, I'm just going to access the first element of the x array, right? So that's the first thing, is put all of your unknowns in an array where each element is a different unknown. Now, what you need to do is you need to keep track of the current guess and the guess from the previous iteration, right? And you know how to do that because we did that with the population code. So at the top of the loop, just save x old equals x or something, so that you have both versions, both the version that was just updated and the version that was last updated, so you could compare them. And then once you have those two, what you're going to do is I'm going to assume that X is the current one, the new one, and it's an array, right? So just to remind you that it's an array, I'm just going to put the vector symbol over it, but obviously when you're programming this, you're not going to use that. You're just going to use the variable name. And then I'm going to subtract X old. That's going to be a vector subtraction, so I'm going to get 3 differences from this, right? Then I'm going to take the absolute value. The function for that in MATLAB is ABS. And that will tell me the 3 differences. And I'm going to divide by, this is actually optional, but it's the preferred method for doing this kind of residual calculation, which I'll explain a little bit more in a second. I'm going to divide it by the X old array. This is because let's say that we were solving a system where the values were 10,000 versus the values that were 0.06. This difference could be very different depending on the magnitude of the values. So by dividing by the magnitude of the values, you're getting rid of that effect, and you're just saying how close they are relative to each other, not how close they are in magnitude. And this condition is going to be set until it's less than epsilon. What's epsilon? Epsilon is a variable that you'll just set up at the top of your code, and it's a small number. So as I think we did one other time, what code did we do that in? We already did a code like this, right? An error code. Oh no, we're doing it in the next 2 labs. So you want these two, the last iteration and the new iteration, you want those 2 values to be close, right? You want them to stop changing. But remember, MATLAB doesn't store the value of 0. It truncates all the way to like 10 to the minus 32 or something. So 0 to MATLAB is like 1 times 10 to the minus 32. So if you wanted to get as close as possible, you would go down to that truncation error. You don't want to do that. That's way more precision than you need. So just set it to some small number, 10 to the minus 3, 10 to the minus 5, and you'll notice that as you decrease this number, it'll just take more iterations for it to get that much closer. Now, I'm going to leave this as an exercise of how you actually program this. So this is going to be the condition in the while loop, right? So the while loop will do the repeating of A, and it will do it until this condition is true. And there's a couple things I want to remind you of when you're writing this code. The first thing is that, remember, a while loop runs when the condition is true, so you're going to have to reverse this condition for the while loop. I'm telling you when you want to, like mathematically, how this algorithm works. This is what you want the algorithm to do, not what you want the while loop condition to be. Second thing, these are arrays, so you're going to have to be careful with your dots. Last thing is that you want to do this for the worst case scenario, so you could take the max of it. So the worst error is what's controlling the while loop stopping. So those are programming things that you're going to have to sort out when you're actually programming this in. But in general, the algorithm is just a while loop, and then your 3 equations, or the one that you're doing in the lab is 7 equations, and then you're just going to plug in the right-hand sides with proper accessing where A and B are set up properly. You're going to put your condition here. You're going to make sure you save your X old before you start changing things. And then you're going to need to update this calculation. So if the calculation is used in here, you'll need to update it at the bottom of the loop. But again, there's a lot of ways to write this, so this is just a general way. The intention of this lab is that you write this in general for any system, any number of unknowns, any number of equations. And I would say about 25% of students write it that way, and that's the goal. However, that is a step higher, a step more complicated than this, writing it for like this exact number. So in your lab, you have to do it for a 3x3, a 4x4, and a 7x7. So some people just write this 3 different ways, one for each of those systems. It's a lot of copy and pasting and messing around with indexing and stuff, but it's your choice what you want to do. To generalize it, I'm happy to help you generalize it, but you just have to start looking for the pattern. So let me just at least get you started on generalizing the algorithm. And then I want to end with just showing you the cost of each method so you have it written down. Okay, so let's start by looking at the pattern here. So this is all going to go inside the while loop, this generalization. The while loop is still going to be the same regardless. Okay, so first you want to look for what's repeating. So do you see how here there's a 1, 1, 1, 1, 1, 1? And if you look at the next equation, all the places where I just said 1 has a 2, 2, 2, 2, 2, 2, 2, and then 3, 3, 3, 3, 3, 3, 3. So that tells you that there's going to be a repeat loop with I going from 1 to n, and you're going to just index everywhere where I just said that there was a repeat with I. So that part's not too bad. To finish the rest of this, you just require another loop. So I'm going to start xi off with just the bi part. That part's easy. And the only tricky part of this algorithm is thinking about this part, because if there were 4 unknowns, there would be 4 terms here. If there were 5 unknowns, there would be, wait, did I just say that right? If there were 4 unknowns, there would be 3 terms here. If there were 5 unknowns, there'd be 4 terms here. So what it is it's a sum, right? It's summing on all these terms. So we've already written a sum, but now you just have to write it so that it changes with the number of unknowns. So j is going to be our sum loop, and j is going to run from 1 to n as well. So that's what will control it. There's one extra one, I'll skip that for right now. But all you do is you just write the sum. So you're going to take the xi and add it to itself, and you're just going to subtract off exactly what you see here. What I'm going to leave for you to kind of think about is how to index this. So remember, the I is this 1, and then the j is going to get you all of these sums. So just think about this. All of these indexes need to be I or j. So I'm going to give you that option to kind of think about it. And then once you get out of the loop, you just need to do the division of this one. And that's all just regular i's, right? They all match. So that one's pretty easy. But I'll let you think about this one. And then I'm also going to let you think about how you get rid of that extra one. So this right here, if I do it for the 3 equations and 3 unknowns, this is what it's going to give me. Assuming I get this indexing figured out, it's going to give me x11, x1 minus x12, x2 minus x13, x3 divided by a11. And you'll notice, you'll notice that in the actual equation, this middle term is gone, right? Because it's the one you solved for. So you have to think about in this loop how to get rid of it. So there's 2 things people do, and I'll let you kind of figure out where to place this. But one thing is people do an if statement, and they only do this if I and j are not equal. If they're equal, then it would skip this. So that would be easy. You just put an if statement around it. The other way that people do it is they just add this term back on right here. And that will also get rid of it. because this term will add it or will subtract it, and then if you add it back right here, you can do it. So that should give you like a little bit to kind of think about as you start this algorithm. This allows you to just write the algorithm once rather than 3 times. So it is the way that I would recommend it. I want to end by just giving you an explanation of cost. So I've used this word a few times in lecture, and now I'm going to define it. So the unit that you need to understand for cost is called a flop. A flop stands for a floating point operation. Floating point means it's that 64-bit number that's defaulted into MATLAB. An operation means that you're doing any arithmetic, subtraction, division, multiplication, whatever. Each one of those operations is the way that we measure cost. So, for example, if you use the inverse method, and this is all generalized to a system of n equations and unknowns, the cost of that method is 4n cubed over 3. So what does that mean? If you had a 10 by 10 system, you would take 10 cubed, multiply it by 4, and divide it by 3, and that would be how many floating point operations an inverse method cost to solve that system. For the elimination methods, the Gauss method, Gauss, like, he has named after all of these things. It's very confusing. They all have the same name, but they're different. That's the method of the elimination and back substitution that I showed you. You can see that that's like twice less expensive. It's not very much. LU decomposition, which I also showed you how to do in MATLAB, is the same cost. And then Gauss-Jordan, which is probably the method you learned in high school. It's typically what's taught for solving systems of equations by hand, is n cubed. So that's more expensive than it's between the other 2 elimination methods and the inverse method. Okay, so the iterative method, do you guys have any idea how expensive that is? So it only is less if you're using a big system. So imagine if this n is 1,000,000. Then the guess and check method is going to be better because it's not going to take as many iterations as it would take the total number of operations to eliminate and back substitute. But you can't measure it because it depends entirely on the system and on the guess that you start with. If you have a really bad guess to start with, which 0 is not a great guess, and that's not the guess that's used, you can't even measure it. But let me just give you this example because it usually makes sense for most people. In a model, let's just imagine you're modeling a fluid system. So you have like the system changing through time. What's happening is this iterative method is getting applied at every time step. So your guess can be what the solution was at the previous time step. So you have a very good guess because it doesn't change that much from like 1 second or from one time to a millisecond later. That makes sense. So that's why these methods are so natural to use in these engineering systems, because you're not just, you have some idea of what the solution should be. It's just changing a little bit through time. So that should give you a little bit of idea of cost. Do you guys have any questions?